I'd like to just introduce one brief definition before going into all that. It is convenient to be able to express an entire Markov chain process, if it's homogeneous, as actually just its set of transition probabilities. And we can do this in a very convenient mathematical form, in the form of a matrix whose number of rows and columns is just equal to the number of discrete states in our Markov chain. So the basic idea is that each entry is a conditional probability of going to some target state given some origin state. And you can see that this is laid out such that the individual entries in a row basically are all coming from the same origin states to different destination states. Therefore, what normalization applies on the entries in this matrix?
The rows sum to that.
Yeah, the individual entries in each row have to sum to 1. So on that very simple basis of how to write down the complete set of transition probabilities just as a matrix, there are actually some useful tools from linear algebra that we can apply. Right now I'm just going to very briefly introduce a basic idea that emerges from the transition matrix idea, which is that you could imagine that there's some distribution, which I'll just call pi, and it has individual components, pi 1, pi 2, pi to pi n, that represent probabilities for each possible state, S1, S2, on up to Sn. And we define this distribution pi as basically being the distribution that is invariant to application of our transition matrix probabilities. In other words, once you reach that probability distribution, applying more steps of our transition probability matrix have absolutely no effect on the probability distribution. Hence, this is referred to as the so-called stationary probability distribution for this specific Markov chain. I think you can see, looking at this short form for the equation, that the stationary distribution is basically an eigenvector solution to this simple linear algebra matrix problem, whose associated eigenvalue is just 1. And of course it also has to obey things like normalization and so on, so you can throw away other solutions that don't have eigenvalue 1 or have negative components, etc. So it is also convenient to rearrange the basic form of this equation, which we can either write in this kind of very condensed form, or we can write out actually how this vector versus matrix multiplication would actually work. So basically what we're saying is, starting from some previous time point, from all possible origin states j, applying the transition matrix going from state j to state I gives us back our same set of stationary distribution probabilities pi sub I. Okay? One convenient way of thinking about this is, you can imagine if we just put in next to this pi I factor this sum, which of course sums to 1 because we're summing over all possible transition probabilities going from state I to state j, over all possible j has to sum to 1. And now if we just make the same, if you will, subtraction from both sides, where we basically subtract the case where j equals I from both sides, we end up with this form here, which has a very simple interpretation. That is to say, this represents all of the probability that is exiting from state I. That is, we go from state I to all states j not equal to I. And on the right-hand side, what we have is the probability entering state I. In other words, originating from all other states j not equal to I and transitioning to I. So this is referred to as the general balance equation, and it represents sort of a perfect balance between the amount of probability that's exiting any given state and entering any given state as sort of the defining characteristic of the stationary distribution. Any questions about this? Okay, well, when we get to more sophisticated sort of Markovian processes like evolution, these questions of stationary distributions and balance both forward and reverse in time will become more useful.
So, I guess on the previous slide it said that, but the tau ij, is that probability of transitioning to I from j, or to j from I?
We defined it as going from I to j.
Okay. All right.
Yeah. Thanks for that clarification.
Can you define the exiting state and the entering state? What was on the next slide? Probability, exiting state and entering state.
You want me to go through this one again?
Or just like, yeah.
So basically, you could think of this equality as having a very simple interpretation. That the left-hand side, you could think of it as the total amount of probability that is passing over all the edges that go from I to some other state j not equal to I. Okay, so we're going from I and we're transitioning to other state j not equal to I. Whereas on the other side, it's the sum of all probability traveling across edges coming to I from all possible state j, again, not equal to I. So it's like a perfect balance going out and coming back in. And of course, this has to hold true for all possible states I in the Markov chain. Okay, as I say, this is kind of the simple intro. We will use this. I think it gets used just a tiny little bit in the homework, and we'll use it a lot more when we start talking about evolutionary processes. Okay, so the Viterbi algorithm, as I said, is a maximization algorithm, solves the following problem. Out of all possible paths through some kind of Markov chain process, we would like to find the path x star that maximizes the probability of the path basically over all possible paths through that Markov chain. And the algorithm is very, very simple to state. We simply define, if you will, a matrix V whose individual elements VTI, where T represents the time step in successive steps in our Markov chain, and I represents a specific possible state S sub I. So VTI means is associated with, you could think of it as being associated with the probability of being in state S sub I at time t in this Markov chain process. And specifically, we define it as being the maximum over all possible states j at the previous time point t minus 1 of this product. That is to say, vt minus 1 comma j times the transition probability for going from state S sub j at time t minus 1 to state S sub I at time t. Okay? And along with this, we also record what value of j actually maximized that specific entry. That is to say, we also store a reverse mapping, which I'll just call R sub t, for a particular state I at time t. We record what value of j actually gave this maximum. Okay? So with those two pieces of information, I'm going to prove to you in a moment that we actually find the maximum probability path up to any specific point xt equal state S sub I. Okay? And the basic way in which we'll do that is by filling out this whole matrix VTI over all possible values of t and I, and also at the same time storing RTI at the same time as we fill it in. And then once we have that complete matrix, we will be able to choose the endpoint that maximizes the probability at the final time step. Let's call that x sub n. And starting from that specific position, let's call that I star, we will look up R sub n I star, and we'll get the value of j star at time n minus 1. And in this way, we continue to backtrack to get the complete path that produced this maximum probability path. Okay? So that's the whole algorithm. It's really just fill in a matrix by maximizing via this purely local rule, and record also the reverse mapping that maximized that local rule. Go to the end, backtrack. Okay. You'll notice that I introduced this to you first for a straight Markov chain, where I didn't say I had any hidden variables versus observable variables. Now I'm just going to generalize this to a full-on hidden Markov model, where we have both observed variables and hidden variables. It's really no change at all. All that we do here is the obvious. That is to say, not only do we have a transition probability for moving from theta t minus 1 to theta t, just as we did before, but now we're also taking into account the emission probability for our observed variable xt to be emitted from our hidden variable theta t. Okay? So pretty much a trivial change. Any questions about how we're extending the Viterbi algorithm to the hidden Markov model case? Okay. So